So in the last video we talked about normal forces as reactionary forces. I wanted to dive a little bit deeper into normal forces and what they are. Let's go ahead and widen this out and make it a better color, something that's easier to read. There we go, normal force. So let's go ahead and define it real quick. Well, a normal force is a contact reactionary force, and it's based off of contact only. And normal forces are always perpendicular to the surface in contact. Let me draw this out to the side so we can tell that it's not part of the term, it's the definition. So let's just sort of tab it out here. There we go, that's better. And you might say, well, Mr. Anderson, what are you talking about? What does that mean? Well, let's go ahead and make a little example for ourselves. Let's say we have this castle wall here. So let's go ahead and call it a castle wall. And let's say this castle wall is under siege. So it's got some big ram driving into it. We'll go ahead and call it a ram. And we can draw the people that are carrying our ram. So they're carrying it, and we got one arm wrapped around the back, one arm wrapped around the front, then we draw another guy. Maybe this guy's on the other side, and he's got one arm wrapped around the back and the front. Then we got one more guy, of course, because there can't be just two guys holding this big ram to break down a castle. And we'll say he's on the front as well, just to draw it quickly. And actually, let me go ahead and give myself a little bit more room to write. So I'm going to move this a little bit to the side. And let's talk about this scenario. Let's say we've got a big force coming out of this ram as they drive it into the wall. So we got the force of our ram. And I won't even give this one a value because I just want to talk about a concept here. But the normal force, or the reactionary force, I should say, that is replying to this, would be a normal force, and it would be perpendicular to our wall. So we've got a normal force fighting it, so F of n. And again, I'm not going to write the numbers here because I just want to talk about the concept. We have two options. Either the sum of all forces equals 0, or the sum of all forces does not equal 0. And these are the only two options. So if this is true, if the sum of all forces equals 0, what it implies, what it tells us, and I'll go ahead and get my text box out to write this out, but what this implies is everything is static. It's in static equilibrium, obviously. Everything is static. Let me make this a little bit wider, but not too wide. I'll just go ahead and stack them on top of each other. Everything is static. Everything is balanced. In other words, or another way to look at it is, or I'll say i.e., nothing broke. And if the other one is true, if the sum of all forces does not equal 0, it's either greater than or less than 0, and again, I'll get my text box out to go ahead and write this out, then it's not static. It's not static. It's not balanced. Or in other words, i.e., something probably broke. And whether it was the ram, whether the people dropped the ram, maybe it didn't break, maybe they just dropped the ram, or the castle wall broke. Basically, it's not balanced. Sum of all forces isn't 0. It's not in static equilibrium. And now to really, really drive home what a normal force is and basically how static equilibrium works when it comes to reactionary forces canceling each other out, I want to do one more example, and I want this example to be just a box sitting on a ramp. Sitting, not a ramp, on a ramp. So let's just draw some random ramp here. Some ramp just sitting here. And let's say we got some random box. Let me draw that a little bit better. Some random box just sort of hanging out on it. Now this box clearly has some weight going straight down. We call this force that's going down the force of gravity. Now, if it's not actually going straight down, it means something's countering it. And you might think, well, obviously it's the normal force going straight up. But here's the deal. It's always perpendicular to the surface. And the surface is going at this weird angle here. So the normal force is also going to go at that weird angle off the y-axis. It's our normal force is going to be perpendicular to our surface here. I don't draw this angle stuff. I'm just going to draw a quick example here. But we got a y-axis here, and let me actually draw that little dotted, but whatever. And again, don't draw this, but basically what I'm saying is this angle is equal to this angle here. But that doesn't really matter in this example because we're not diving into calculating the normal force and the force of gravity and all that. I'm just making a point here. If you look at this example, we see that the force of gravity is going straight down, but this is not going straight up. It's going slightly to the right, which means the sum of all forces in the x direction can't be zero if these are only forces. There's something going to the right and nothing going to the left. Well, you might say, well, things sit on ramps all the time and don't slide down. Sometimes they do, but sometimes they don't. What's stopping that? Well, because there's another force going to the left here, and that is another reactionary force we will call the force of friction. And either the force of friction is strong enough to hold this box in place, or it's not. But if everything, and let me pick a better color here, just to get it off from that side, and it's still not the better color. Let's just go with gray. If everything is static. Meaning the box isn't moving, then we know the sum of all forces equals 0. So I know if this isn't moving, then all of these forces cancel out. I don't need to calculate them because I know they all cancel out. Unless I was curious on what they equal so I could do some random math, or I was asked to calculate the normal force. There's not much to calculate because I know the final answer. The sum of all forces is 0. That means the sum of all forces in the y direction equals 0. All forces going up and down, and all the forces going left and right. The x direction equals 0 as well. And again, we could calculate this out. We could say, well, there is a y component here and an x component here, and we could calculate what each one is, and then we can calculate the x and y component here as well. And we could just then add them all up and cancel them all out. But if everything's moving, if nothing is moving, I mean, if everything is static, then they have to equal 0, and that's the idea. I'm going to go ahead and get rid of those arrows. I don't want you to draw all those, but yeah, that's the idea.